While we wait for our guest has already arrived. So I'll just mention one thing. Do check our chat box. You'll get the links for social media and do follow us to stay updated about all our events.
So today is going to be very exciting as we are going to dive deep in the world of AI. From exploring the field of computer vision to complex data in AI, we have got you all covered. This is Ishika Kulkarni, second year CSE specialization in artificial intelligence and machine learning student.
And I am Abid Datta, a second year student, CSE Core, and we are the hosts for today's event. Yesterday, we discussed convergence of AI, sustainable Internet of Things, and Ashtanga AI, and AI stack for complex ecosystems.
Sir, you have to give the welcome address, so I have informed. Okay, 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 okay.
In today's session, we are back with even more thought-provoking topics. We will be exploring visual attention model followed by a conclave session on industrial aspects of AI.
Then, we'll look into a new aspect for building a better future and finally explore the role of AI in healthcare. As we already know, the applications of AI are limitless, and therefore, there are ample opportunities lying ahead for us. And through today's session, we'll dive deeper into the world of artificial intelligence.
I would like to thank our respected faculties who are present here. And with this, I would like to call Dr. Soundarajan, our program chair of BTech Artificial Intelligence and Machine Learning with us today.
Yeah. Ishika, I am audible?
Yes, sir.
Yes, sir.
So I'm welcome to all the participants for this workshop, as well as I thank VIT management and respected Vice Chancellor sir and our department dean sir, Manas Kumar Mishra, and Nageshwara Gupta sir. They are given a support to conduct this such an event for a big thing for overall India now. So everybody is talking about artificial intelligence and machine learning. So now I welcome our esteemed chief guest today for the meeting, Dr. Krishna. So he's began his research in 2011, and he actually completed a lot of international publications. He has been invited 10 plus IEEE conferences, given presentation at UC Berkeley, CNRS, MIT, NTT, Tokyo, and many reputed institutions. His research interests including computer vision and cloud processing, pattern recognition. So the list is going on. So he has having two patents in this field of computer vision. So I welcome you, sir, for this great occasion of the Artificial Intelligence Conclave. And I welcome all the participants and the coordinators of this event. So this particular session is more enlightened for how the computer vision applied for various industries and various applications. So thank you, sir.
Thus, without any further ado, we call Dr. Onkar Krishna.
Am I audible?
Yes, sir. You're audible.
Okay. Thanks for the invitation, and it's really my pleasure to talk to all of you. And so, let me share my slides. Can you see the slides?
Yes, sir.
Okay. Yeah, so thanks a lot for organizing this talk today. And it's my pleasure to talk all of you. And I will actually explain some kind of little bit detail about some techniques in the computer vision and all. So today's title for my talk is Visual Attention Model. But before going deep to the research, first let me briefly explain about myself. I actually graduated from in India. I got my degree from Triple IT Jabalpur, and after that I moved Tokyo University for PhD, and I completed my PhD in 2018 March, and since then I actually working in a research lab in NTT, and my research interest is in computer vision, deep learning, and machine learning. So yeah, so mostly I'm talking about initially some fundamental computer vision and then some applications of the computer vision. So let's start the today's talk. So first I divided the today's talk mainly in two parts. In the first part, I will talk about the deep learning based model for 2D image. So you see there are like lots of images around you. So if you are going to work in the computer vision, you will deal with the images, 2D images. So first part is very simple, like I'm going to talk how to apply deep learning on the 2D image. And in the second part, I will discuss about the recent progress of deep learning with some 3D data, 3D point cloud data. So, there are lots of devices nowadays. You can easily capture the 3D information. 3D information means like in the 2D image, you do not know the depth of the object inside the image. So you cannot measure like how much distance particular chair is from the another chair. But if there is 3D data, you can easily capture the distance, and you can easily capture the depth. So that's why 3D data is like quite important, and these days actually capturing 3D data is quite easy. So applying deep learning on the 3D data is like kind of very growing field. So I will introduce that also. And in both part, I will talk about some state of the art method for object detection and search from 2D image, also from the 3D data. And I will briefly introduce some of my recent work for image search. And also there is one part about saliency prediction. If I have time, I will quickly introduce what is saliency and how we can predict that. So let's go to the first part, where first I will discuss the popular work of the visual attention model for 2D image. But before that, I will explain, of course, what is visual attention model, and then I will explain the work, and then I will introduce some of my work. So, so actually, my purpose is like not to just explain the theory. I want you to, I want you, all of you, to actually implement the concept. So I will actually explain some data set which you can download, and also I will tell the link of the code which you can download and run. So let's start with the data set. So for visual attention model, I'm going to talk about the two very simple data set, which all of you might know. The first one is called the augmented MNIST. So all of you know the MNIST data set. MNIST is like the data set of the numbers. So 2, 3, 0 to 9 numbers. And augmented MNIST means like there are the numbers, like you can see in the image on the top first one. So you can see there are like numbers 0, 1, 2, but with the numbers there are so many noise, like there are white patches, and the task is to determine what is the number inside that image. For example, in the first one you can see there is 0, and the second one you can see there is 1, and the third one you can see there is 2. So what we want here, the computer vision model, to give these images as an input, and in the output we want to determine, okay, this is 0 or 1 or 2. So like that way. So this is like kind of very simple task which we are going to solve with the convolution neural network, and after that which we are going to solve with the visual attention model. So I will explain that. And the second data set is going to be a little bit difficult, which is called street view house number, in which actually you again have to determine what number is written inside the image. So input will be this image, and the output will be the number of the street. So the number of house number. So you can see in the first one, the output will be 379. So there is some order of the numbers. So the computer vision model should determine the numbers in that order. So I'm going to talk about for these two data sets, first the very simple CNN models, and then the visual attention model, how the problem can be solved by the CNN, and then how the problem can be solved by the visual attention models, and why
Sir,
we need.
just a second, sir.
Yeah.
Sir, the slide isn't changing.
Oh, sorry.
Sir, try sharing your screen again. It will work then.
Okay.
Now it's fine, sir. Now it's fine.
Okay, let me do it again. Just a minute. How about now? Can you see?
Yes, sir, it is
Yes,
visible.
sir. It's fine now.
I'm changing the slides so you can see all the slides.
Yes, sir. It's changing.
Okay, okay. Okay, so I think let me start from the beginning, or it's okay. Okay, so I can actually quickly summarize what I said. So this is the data set which I was talking about. So I said like I'm going to. So can you see the images like
Yes,
augmented
sir.
and okay.
Yes, sir.
So I'm on the slide number 5 now. So yeah, so I what I said is actually I'm going to talk about some basic data set first, and this is like very simple data set which is called MNIST data set, and I'm going to use the augmented MNIST data set. Augmented means like there are the numbers in the images, but there are some noisy patches also. For example, in the left image you can see there is 0, but you can also see the some noises there. And the task for the computer vision model here is there is the input, this image will be the input, and in the output we want to find what number is in that image. So that's the task, and we are going to solve this task by using the computer vision by using the CNN. And then I'm going to tell about like why we need to replace the CNNs, or why we need some visual attention model to solve the same problem. So that's why I'm introducing first the data set. So these are the two data sets which I'm going to talk about. And the second data set I'm going to talk about the street view number. So where again the task is to find the numbers inside the images, but in a particular order. So these are the two data sets which you can actually download and you can try by yourself also. And the reason for choosing this simple data set is like this is very good starting point, not just to understand the CNN or the visual attention model, but also to implement them. So you can start with these two data sets. And yeah, in this talk actually, so for both data sets, first I will talk about the very classical CNN approach to solve the problem, and then I will introduce the visual attention model for the same. So for MNIST dataset, first I will discuss the very simple approach based on the two convolution neural network, and then I will introduce a famous work based on the visual attention model. So let's go one by one. So this is for the first dataset, which is augmented MNIST dataset. So as I said, the task is to predict the digit inside the image. So this is very simple task. So so how we can solve this? The very simple way is like just you can use like any programming language like or any programming tool like Keras or TensorFlow. You just create the two convolution neural network layers and you give input that image, and that actually two convolution neural network, of course followed by some max pooling and all these, and these two convolution neural network can give like 99% accuracy if this is just MNIST, not the augmented MNIST. If there is no noise in the patch, then you can like 99 with 99% accuracy with just two convolution neural network you can actually predict the what is the number inside that image. So but if there is some noise, and if I'm going to use again the two convolution neural network, that the accuracy will be in the right side, you can say is 50%. So because the noise actually create the disturbance, so the task become a little bit more difficult. So just using the two convolution neural network cannot solve the problem. So the accuracy is just 50%. But actually you can increase this accuracy by increasing the number of convolution neural networks. So if there is only two, then the accuracy is low, but maybe if you're using 5 or 6 layers or 10 layers and there are so many max pooling you are using, and after each layer, and then you can increase this accuracy. So this is how we can solve this problem of detecting a number from an image by using the convolution neural network. So everything looks good. Like for this task, the convolution neural networks works very well. So but the thing is, like, then why we need the visual attention model here? So although we can achieve very good accuracy by using the CNN models, but the problem is, like, the when we apply the convolution neural network to an image, it's very expensive. So expensive means, like, the computational complexity is very high. The reason is, like, when we convolve the filter map, so convolution neural network, what it does actually, so for an image, it convolves a filter for all the pixels. And convolving means it multiply the filters weight with the image pixels, and it do this process for all the pixels in the image. So that's actually very complex, computationally complex. So if the image is very small, then it's okay. But for example, if the image is very large, so nowadays you see the, the you can see there is in the Mars, there are images. So those images are Mars images. The space images are like quite huge. So if you want to process that kind of image, or even the simple image, like like the home image or the satellite image. So satellite image have like many pixels. So if you want to apply the convolution neural network on the satellite kind of image, you need to apply that convolution neural network to all the pixels, and that's very time consuming. And even if you're using the so many GPUs to process that kind of image, even just for the training, it takes like several hours. So that's actually not very desirable, using directly the convolution neural network to solve the problem. So the very general idea how we can improve the like the time complexity is by simply learning from how the human eyes work. So so you can see the slide number 8. So now I'm on the slide number 8. On the right side, you can see an image. So in this image, that so this image is basically how the person looks the image. So you can see starting from the 0. So first he start looking at the 0, then move to 1, then 2, 3, 4, 5, like this way. So a person do not process all the image from the left to right. It only process like very few locations. So you can see if we look some image, we look only few locations. So the idea is like how we can develop a convolution neural network which do not process all the locations but process only few locations, like in this picture. So from there, actually, the visual attention model comes in picture, and this is the image you can see. So this is how the convolution neural network convolution approach works. So here you can see we have a filter and we have an image, and the filter is, I mean, we are in this image, you can see the filter is applied on all over image, and this actually is very time consuming if the image is very large. So we need some kind of very smart approach. So that's why the visual attention model comes. So you can see in the second image, the filter is not applied everywhere. It's applied only to the few locations. You can see it's moving from one location to another location, and then it's determining the what is object inside the image. So that's the fundamental difference between the convolution based approach and the visual attention based approach. So the visual attention based approach do not apply the filter to every location, but apply filters to only very few important locations, and then determine what is the number written in the image. So in a very simple way, so for both of them, the input is the image and the expected output is what is the number inside the image. But the process to solve this problem is little bit different. In the first image, you can see the convolution is applied everywhere. But in the second image, you can see the convolution is applied to only very few locations. So that's the basic difference. So let's see how the visual attention model is implemented. So I'm not going to very much detail. So now I'm on the slide number 10. So yeah, let me know if you cannot see. So I'm on slide number 10. So you can see here I'm going to talk about the basic idea which is like this work is called the recurrent attention model. This is like very popular. Actually, you can download the code and dataset from their website, and you can simply implement it and try it by yourself, and you will learn lots of things in this work actually. So let me discuss what this work is. So as I said, like this work is inspired from the human's visual attention. So how the human look the image. So this is inspired from that. So how we can implement that kind of functionality which is in the human's visual attention into the computer vision model. So the first thing is like we wants to look at the image at the particular location, and at that location we grab some information and then move to the another location, some another place. So the first thing is like how we can grab that location. For that actually there is glimpse sensor implementation. So this implementation is basically the input is the location, some location, and the image. So location is inside the image. So at that location in the image we actually crop some window. Like that window is basically we are looking inside, and that window actually go and after that once we crop that window, and that is called the glimpse sensor. Basically sensor means like at the very center location where exactly we are looking, the resolution is very high, but as we go far from the center the resolution is very low. In this way actually the sensor works. So that's called the retina representation of the image. So once we have the retina representation of the image, then we comes to the glimpse network, which is the second part of the implementation. So that representation goes, so we apply some kind of fully connected layer. So fully connected layer means like we multiply the image with some weights. So you can simply understand in the layman term. And once we multiply that retina representation of the image at the particular location with some weights, so we get some features, and those features actually we use as a input to the model. So in summary, this is how the model works. So it seems very complicated, but just let me break down how it works. So there is two parts in the model. So you can see the left part and the right part. So the left part is basically, so the purpose of the left part is to extract the features at some particular location, and then based on those features it goes on the second part, and the second part actually determines okay where to look next. And in that way actually this there is a dotted line connecting from the first part to the second part. So once we extract the features of the image at some particular location, then that features work as an input for the second part, and the second part again look for the image, and it determine what is the number inside that image, and also determine what should be the next location to look for. So this is how actually our eyes work. We look at the some location, and then we capture the information at that location, and based on those information we move to the next part, or where to look next. So that's the way this actually algorithm was implemented. And in that way actually it makes everything looks very simple. So it just go from one location to another location. So you can see there is red bounding boxes. So these red bounding boxes are like the location. So one location it look, then move to the next location, then next location, and finally determine okay this is number 5 without going all the locations. So in this way actually you can actually download this code and dataset both from this link. I will share this slide on my homepage from where you can download and try all these algorithms, and you can get like very good accuracy, like around 98%. So yeah, so the whole purpose of this part was to explain how to implement a very simple task by using the convolution neural network, and then how to improve the computational complexity of the convolution neural network by using the visual attention model. So I hope that now you understand what is the difference between the convolution neural network and the visual attention model. So the visual attention model pay attention only to the important regions, not to the all the locations. So that's the basic difference. And let's go to the second data set, which is actually the now the repetition. Now here again, so we have to find what the numbers written in the image. like you can see 37961,972, but here there is not just one number but multiple numbers. And because this is the real image, so the if you input this kind of real image to the neural network, because in the real image there are lots of the illumination changes, contrast changes, so so we need like more complex convolution neural network to solve the problem. So the main idea is to look at the multiple digit at the same time and to classify the digit sequence into fixed length digit in order with the blank padding if the data is missing. So you can see how we can solve this problem with using the convolution neural network. So here you can see there is 1 2 3 4 5. So we have like four three convolution neural network followed by some rectilinear unit and then pooling unit, and then there is final fully connected layer, and after that there are like 1 2 3 4 5 dense layers. So basically dense layer classify the input into the different numbers. So just by using this kind of three convolution neural network and then fully connected layer followed by a dense layer, you can simply get the output like very good accuracy just by using this kind of very simple convolution neural network, and you can get 87% accuracy for this task. But on the other way, you can also use the visual attention model for the same task. So this is the visual attention model which I explained. This is a little bit different from the previous version. So this is like this is the Google DeepMind paper. So you can actually download the code and everything, and you can see how it works. So it actually again is the same. Like it take the input image and it look at the some location and extract all the information at that location and then determine what should be the next location. So in that way actually it very smartly it actually solved the problem instead of going to the all the locations. So this is the example of the updated version of the recurrent attention model, which is called deep recurrent attention model. I'm not going to in detail of that, but if you're interested you can actually download the code and dataset, everything available on their website. I will share the link. And after this I'm going to talk about like our research, which is our research, which is deep reinforcement learning template matching. So what is reinforcement learning? So let me explain some very basic concept of the reinforcement learning. I think you know the supervised learning. So in the supervised learning, you always provide some kind of information. For example, if you have to identify what is this image, like cat, dog, donkey, what's that in the image, then your network, there is a convolution neural network, it predicts. Predict means it gives the probability of this image, like it may be 40% cat, 90% cat, 70% dog, or like that. And based on that probability you determine, okay, the highest probability is the cat, so you say, okay, this image is of the cat. So that's how the convolution neural network work. That's how the supervised learning work. So supervised means like if you already know this is cat or not cat while training, and then if the network predict this is dog, then you provide some feedback to the network, no, this is not dog but this is cat. And based on that feedback in the convolution neural network, which is simply the weights, so those weights are modified. So after modifying the weights, the network again actually predict the output. So in that way, and then again it predict, okay, this time cat 70% and like dog 10%, like that. So this time it's correct. Okay, the higher probability is the cat. So we tell the network, okay, this time it's correct. And based on that information, network actually update the weight. So this time the networks do not need to update the weight. So in that way actually the supervised learning works. But what happen if if we do not know actually this is cat or not cat while training? So then actually that's called the unsupervised learning. But in between the supervised learning and unsupervised learning, there is another learning which is called the reinforcement learning, where actually we do not know what is the right answer while training. So we do not know exactly this is cat or dog, but we can give some kind of reward. So for example, in the second image you can see there is input, this game, and the convolution neural network predicts run or jump, only two output. and we do not know which one is good, running or jumping, which one will actually solve the problem, or which one is good after the long run. So based on that, actually, after some time we provide the reward. Okay, running actually may be good in this situation, and it actually gives some kind of reward to the network, and based on the reward, network updates the weight. So in the right side image you can see a brain here. So the brain is the neural network, and this environment, so the world picture, you can see the globe. So the globe is basically the environment. So what happens, environment means like the, for example, what is the input is the environment. So for example, the input is some kind of image, and that is called the observation. So you can see on the left side there is observation means the image at some particular situation, and then the brain is the neural network. So the neural network gets the observation, and then based on that observation it predict what should be the next action. So it do not predict actually what is the class of the object, but it predict what should be the next action, and based on that action, actually that action is applied to the, again, to the environment. So after jumping, after this, in this game, after jumping, it moved to the next location. So next location, there will be the different environment, there will be different image, and based on that, actually it gives some reward. Okay, this jumping was good, like this is in the right direction, so the neural network gets some kind of reward. So based on that reward, neural network understand, okay, I'm doing good, and it again move to the next location, like that way. So in this way, actually the reinforcement learning works. So the reinforcement learning actually work based on the reward, not based on the exact class. And I would suggest, if you are interested in the reinforcement learning, you should use this open AI spinning up. So this website have like very simple introduction how we can simply implement the reinforcement learning, and why this is important to learn the reinforcement learning. Maybe you know the autonomous car driving and all this. So most of the autonomous driving project, they use the reinforcement learning to solve the problem. So if you are interested to work in the autonomous driving, then you should start by learning what is the reinforcement learning and how to implement very simple algorithm by using TensorFlow, Keras, and all these models. So if you are using TensorFlow 2.0, the latest version, then like you can solve the reinforcement learning problem within few lines. So I would suggest like you should start with this kind of like tutorials. Not only this, but you can choose some very simple tutorial, and where you can implement, where you can learn what is the reinforcement learning and all. So yeah, that's all about the reinforcement learning. Very simple, very brief explanation. So now I'll talk about my work, which is based on the reinforcement learning. That's why I introduced what is the reinforcement learning. And also this work is very similar to the visual attention model. So this is the combination of the visual attention model and reinforcement learning. So what we are doing in this work is, the task is to find this query in this image. So we want to capture the bounding box. We want to find the bounding box where this query is inside the image. That is called template matching. So we want to find the exact template in the image. So how we solve this? So there are many actually research. If you look, there is shift called kind of features, and there are lots of research to solve the problem. And very fundamental research is like, if you have some query, you want to find that query in the image, you look for that query from left to right and top to bottom, all the locations. That's very like time consuming method, but there are many updates for that method, like pixel subsampling, window skipping. So you skip some window, you do not match the query with all the window, but you match the query with very promising windows. So that's the another way. So but what we did actually, but all these actually techniques still like takes lots of window to compare and to find that query. So how we do very in the fast way? So this is our idea. So we use reinforcement learning. So for example, we have this query on the left side, and we want to find this query in this image. So we search for this query from one location starting here, and you can see there are dots. So these windows are actually searching for this query. So you can see this query is on top of this food market building, and we are not looking every location in this image, but we are very smartly, our algorithm looks at the very bottom, then moves up, then moves up, then moves up, and finally it finds this query inside the image. So in this way, actually we can computationally save lots of like computation we can save by using this kind of strategy. So and how we implemented this kind of algorithm is, the idea is like very much inspired from the visual attention models. And also we applied, we do not actually use supervised learning for training this kind of algorithm. We use reinforcement learning to train this this problem. And let me explain how the model actually, what is the model, what the model is. So we have this query and we have this reference image. We want to find this query in this reference image, and there is CNN based feature extractions. So you can just simply use some kind of like CNN, simple CNN model, and the query goes as an input to the CNN model. And there is a window, in the red window you can see that only that information goes as a another CNN, and output from the CNN is the features of the query and the features of the window. And then these features are combined and goes input to the LSTM. So LSTM is kind of, it's a recurrent model which actually can remember. So there is a memory in the LSTM which can remember what is the previous state. So the input goes to LSTM, these two features, and also the current location feature goes as an input to LSTM, and LSTM actually predict what should be the next location to move. And then at the next location again it extract the features and then move to the next location. So in this way actually this process gets repeated until we reach to the target. So that's why very efficiently we can reach to the target by using this very simple implementation. And these are the details. Maybe I will just quickly explain and then skip. So for example, in the supervised learning, as I said, we already know what is the exact location of that query inside the bigger reference image. But in the reinforcement learning, we do not know the exact location, but we know what is the, like for example, um, what is the actually the right output. For example, uh, inside, so if some robot is searching some object inside the house, and it goes and okay, you say like, please find me a cup. And then the robot actually goes and finds some other object and come back to you, okay, this is your cup. So you say, no, this is not my cup, this is some other thing. And you give reward. Okay, your reward is 0 because you found something wrong. And based on that reward you train the network. So you do not train the network by providing the exact location of the cup. You train the network by telling what is right, what is wrong. So that's how the babies learn. So in that way actually this network is trained. So we train this network by providing the reward, okay, this is the correct and this is incorrect. And just based on this information, so correct means once our network correctly find the template, we say we give reward 1, otherwise we give reward 0. And that way the network weights are updated, and we learn the very efficient search path. And these are the data set which I used. We had the query and we had some kind of reference, and our aim was to find this query in the reference. So actually we achieved like quite good accuracy, like almost 90% for very cluttered MNIST data set. But if we compare with the baseline method, the accuracy is not that good. And this is the time actually. So the most important thing is like we wanted to save the time. So you can see in the right in the boxes, so there is only 6 number of steps to find the object. But if you see the baseline method inside the bracket, there are like 2809 steps to find the object. So the change is like very incremental, very significant. So in that way actually this kind of visual attention approach is very important to solve these kind of problems. And this is how it actually works. So for example, if we have this query, this number, and we start at looking this number at some, so these dots are the locations where our algorithm looks for this number. So it look at some location, then move to the another dot, that is another location, then finally the red dot is basically the final location where it actually find that object. And then there is a crop, so we crop at the red location, the red dot, and that crop is basically our output. So you can see here the output is like, we cropped that bounding box and we actually found that object. So in that way you can see there is search path. So this search path is like quite simple. I mean, we are not exploring all the locations to find that object, but we are actually exploring the only particular locations. So that's how our algorithm works. And that's about the 2D image. So that now from the 2D image, as I said, like I moved to the, I think I still have 15 minutes maybe. Yeah, I will move quickly to the 3D point cloud data. And so what is the 3D point cloud data and why we are interested in working on the 3D point cloud data? So actually I would suggest, or I will try to motivate all of you to start working on the 3D point cloud data, because in the 2D, if you work on the 2D image, there are lots of algorithm to solve the 2D image problems. But if you work on the 3D point cloud data, this field is still like, there are lots of challenges to solve in the 3D point cloud data. So there is lots of scope to work on this. So in this part of my talk, I will introduce some open source data set which you can download for 3D point cloud data, and some open source algorithm which you can apply on the 3D point cloud data. So the task is again same, like you want to detect some kind of object inside the 3D point cloud. So what is the 3D point cloud? Let me explain first, and how it captured. So for capturing the 3D point cloud data, maybe you know about the lidars. So we use lidars to capture the 3D point cloud data. And yeah, so as I said, what is the point cloud? So the point cloud is basically, it capture the external surface of the 3D object, and we can capture that external surface by simply using some lidar sensor or RGBD camera. And in summary, actually, the 3D point cloud is just a collection of the 3D points. So the 3D point cloud is actually nothing like nothing something like very big thing. It's just a simple collection of 3D points, and it's mostly actually collected for the indoor scene and the outdoor scenes. And this is how the lidar works. So now I'm on the slide number 31. So basically the lidar sensor act like a bat. So you can see the bat using like some echolocation to determine where the object are. So basically it sends the signal, and that signal actually collides with some kind of object and reflected back to the bat, and then it determines how far that object is. So that's how the lidar works. So the lidar actually suits the pulses of the light, which bounce off the surface and return to the sensor, and then sensor calculate the time it took for the ray of the light to return and which direction it came from. So this is basically, this process is ultimately to create the point cloud map of the scanned surrounding. And the best part is that the point cloud will store every detail down every detail of the particular location. But there are some limitations of the lidar point cloud, which I skip here. You can see actually the lidar is like, not very good for capturing the very fast moving objects, and like if the surface is very reflective, it cannot capture. So yeah, as I said, like if you want to work on autonomous driving cars, then you should deal with this 3D point cloud data. And the real life example is by using, the Google Waymo car. So the Waymo is actually used for they use high frequency lidar sensor on top of the car. And then based on that lidar, they create the map of the environment. And based on that map, actually, they try to navigate this car by using just like, computer vision model. And also maybe about discovery of some civilization in the Guatemala, and actually this was happened by using the lidar sensor, because the lidar sensor can capture the very detail of the environment. So once you know the very detail, there was a helicopter was running on the Guatemala, I mean the forest around there, and they were capturing the lidar point cloud data of that forest. And by analyzing the data, they found there is some kind of civilization there. So the working on the lidar point cloud data is like quite interesting, because you can get the very detailed information of the environment. And how we can, so these are the open source point cloud data, or the lidar data, which you can download. They are publicly available, and you can just download and start working on that. And what will be the first challenge? The first challenge will be like, the point cloud data is very huge. So if you want to apply the lidar if you want to use that point cloud data as it is, that will be very complex. So for example, in this you can see the original point cloud data is 8 million, and using 8 million point cloud data, then what will be your matrix size? So your matrix size will be 8 million by 3. And if you input that 8 million by 3 matrix into your computer, into your network, and it will multiply that matrix to the so many weights, and that multiplication will be really very complex. So we actually, the first challenge is like how we can use that point cloud data with the neural network. First, we need to downsample the data. So how we can downsample the data? So there are many techniques, and these are just one line codes you can find in the Python for downsampling. So first you download the data set and then apply this random sampling. So the random sampling just randomly find some point and remove those point. So you can that way decrease the points, as you can see here. So this is the lighter point cloud data, and then applying the random sampling. And then another sampling is like more smart. So not randomly select the point, but you select some, spatial, like you measure the distance and select only those locations which are like which will not disturb the structure. So for example, if you randomly sample, it may actually disturb the organization of the image. So that's why it's required to do the spatial sampling. And the another way is the voxel grid sampling. So these sampling codes are just 1 or 2 lines in the Python. So first you download the data set. Because the data set is very huge, so you apply some kind of random sampling, spatial sampling, or voxel grid sampling to decrease the size of the data set. And once you decrease the size of the data set, so yeah, I will explain what you do. So this is also another open source data set. Actually, in this data set, you can use this website, go on the website, and then you can select the region of interest which you want to download. And then this actually website will download the point cloud data set of that region. So of that satellite region. So from the satellite, you can found the, you can see in this GIF. So you can download the satellite image, a satellite point cloud data set of the particular region by using this website. So this is open source, so you can try from this data set also. Yeah, so and this is another one for driving. If you're interested in the autonomous driving, you can go to the Kitty LiDAR data point cloud data set. You can download this data set also. And then you can, once you have the point cloud data and you downsample the data set, and then you need to apply some deep learning algorithm to the point cloud data to obtain the, in the image. What we do, we recognize, okay, there is object in the image or not by using some deep learning based method, or we try to segment the image by using the deep learning method. In the same way, we want to detect the object in the point cloud, and we want to do the segmentation with the point cloud, and we want to do all the things which we can do by using the deep learning in the 2D image. We want to do all those things with the point cloud data. But the problem is, applying you cannot use the, you cannot use the same 2D image based method for the point cloud data, because 2D image is like is just 2D, and 3D point cloud data, there is 3 dimensions. So simply, if you want to use 2D image, 2D object detection method to the 3D point cloud data, it will not work. So that's why there are like many people working for the 3D point cloud object detection, 3D point cloud object search, 3D point cloud object tracking, which is completely different from the 2D counterparts. So I will very quickly, I think the time is like just maybe 10 minutes. So I will, or maybe less than that. So I will quickly say, yeah, you can just, maybe I skip this slide. So you may be familiar about 2D image and 3D point cloud data is like very sparse, like, and while 2D is quite dense. So applying 2D is like not good, not possible. And this is the way how we can do very simple work. So for example, the input is here, not image, input is the point cloud data. And the output is basically the bounding box, like which bounding box means like we want to localize the object inside this point cloud data. Localize the object means we want to find the bounding box which fit around the object. So that's the purpose. So input is the point cloud and the output is the bounding box around the object. And this is the network. So if this is image, we can just solve this problem by using the CNN or the visual attention model. But because this is not image, there is 3 dimension. So what we do, we divide that point cloud in the form of the image. So we divide into the voxels. So if this is image, we say pixels, but this is the point cloud data, so we say this is the voxels. So we divide into the voxels, and those voxels goes as an input to the 3D CNN, and then the 3D CNN extract the features, and then we apply those features to predict the, and then those features goes to some reason proposal network called SSD, or like very famous networks, and those network actually predict the bounding box around the object. So that's how these 3D point cloud things works for object detection. So this is one more popular work which actually input the point cloud data, and output is the bounding box around the object inside the point cloud data. So you can see there is a output, prediction output. You can see the output is the bounding box around the object. So I skip the detail of this work. So this is the GitHub code for trying all the point cloud object detection methods. So they provide very nicely like written code for very latest algorithm for the point cloud data. So you just need to simply go to this website, download the point cloud data and download the algorithm. You can download the weights, and you just try by yourself to run this code to detect the point cloud object inside the LiDAR point cloud. So I would say like you can start learning about the point cloud data from this website or from this codes. So you can run all these things by yourself. And yeah, we work on the point cloud data also. So this is like we wanted to search some object inside the room. In the room is actually the point cloud data. So we want to find this marker inside the room. So the thing is like we do not want to search all the places. So we develop algorithm which actually search very few locations like this way and find the marker. So that's our actually key idea of this work. And so basically we learn the search path. So we do not just learn to find the object, but we learn what path will be the shortest path. So this is how the algorithm works. And due to the limitation of time, I will just explain. So this is the okay, let me explain this slide. And this, so for example, we have this query, and this is the gallery means the room. So we want to find this chair inside this gallery. So before I was talking the image, but now I am saying the gallery. So because we have now depth information also. This is not the image, but this is the point cloud data. So we are saying this is the gallery of the room, and this is the query is also the chair and the point cloud of the chair, not the image of the chair. So now we cannot directly use the CNN. We cannot directly apply the CNN to this point cloud data. So we use some special network which is called PointNet++. The PointNet++ is like a very beautiful architecture. So you just give the point cloud as an input, and it extracts the features of those point cloud and try to find what object that point cloud is. So we use PointNet++ to extract the features, and then based on the features, we determine what should be the next location. And in that way, actually, we try to find the object by moving from one location to another location. So that's the gist of, the summary of this implementation. So yeah, so these are the some key points how we do that. Yeah. So I would say like you should first try point cloud, downloading the point cloud data and running the point cloud object detection method by that website, which I should be by the GitHub page. And yeah, this is how we learn. So for a query, this is the search path. You can see our algorithm actually starts some location, then move another location and try to find that object. Yeah. So that's, I think, all for today's. And the last topic I will skip. Yeah, that's all for today. Yeah. Thanks a lot. If you have any question, please.
Yes, sir. If anyone has questions, they can ask in the chat box, or they can just simply unmute themselves. Someone said in the chat box, your paper on translating an adult's focus of attention to elderlies was very interesting. How do you think it can impact society? Do you think it's feasible in India, or is it ready to implement here?
Yeah, I didn't explain this paper, but it's actually, let me briefly say what this paper worked. So, focus of attention. Focus of attention means like if you're looking some image, so you are not looking, if you are looking around your room or around surrounding of yourself, you are looking at some particular location. You are not looking all the places. So the place where you are looking is called the focus of attention. So what the computer vision model does actually, that surrounding goes as an input to the model, and the model try to predict what will be the focus of attention for that image. So that's the model, that's how the model works. But all the models are made for the adults, so the adults looks quite different from the elderly people. So we developed a model which can actually predict the focus of attention of the elderly people by using the simple image to image translation method. So this kind of algorithm can be used, for example, while doing the autonomous driving. If our algorithm can predict where the elderly people will look, then it can actually avoid some kind of accident or something like that. So we can actually we can suggest to the driver, okay, this place may be dangerous for you, so be more careful for that. So if we can predict the focus of attention of elderly people, we can solve many problems related to the elderly people. So yeah, that's kind of very helpful. If we imagine like anywhere, not just India, like anywhere the elderly people population is like going to increase, like in Japan it's already high. So yeah, it's very useful.
Okay, thank you, sir. Our
We
next
have another
question.
question
Yeah.
from Om Vitalkar. It says, Sir, can you please link up some sources or articles to study more about 3D point cloud data? Or can you please suggest any book?
I would say for 3D point cloud data. Okay, so the best thing is like, not to just read the 3D point cloud. What is 3D point cloud? How we can work? You can start by implementing actually. I would suggest all of you not just reading the theory about the concept, but you can just go to this website, yeah, this GitHub page, and there are like lots of papers. So on the left side you can see the papers, so the point pillar, second point RCNN. So these are the papers, the very famous state of the art papers. And the task for all these papers, the input will be the point cloud data and the output will be to determine the object. So if you use these papers and try to read these papers and implement them, then you can then you can understand the concept very fast, instead of reading from the very basic. So you can just try by implementing, and it's kind of back propagation. So back propagation means you try to implement and then try to learn how to solve the problem. So I would say like first you can try with this web page, and once you read the paper you maybe do not understand many terms, then you can go back to the Google to find what exactly that means. So I actually do not know the exact any book to start with the point cloud data, but this website is very useful. And also this code is also, and this website is also very useful, like this one, to download the data set. So you can go to the website and directly you can download the point cloud data, and then you can see by using the Python code how the point cloud data looks, and you try to visualize it by using the Python libraries. So then you will understand a lot about it. So that's the way. I mean, I would suggest like try to, instead of reading, try to implement things. Yeah.
Okay, thank you, sir. Our next question is from Chaitanya. What do you think is the most essential focus students should keep in mind when pursuing their degree?
I would say, like in my experience, of course, the grade is important, like how much grade you are getting. Like, I'm not sure how much important, but the most important thing which industry people are looking is like how many programming language you know and how many projects you did, like how many real life problems you solved by using the deep learning, by using your whatever field you are working on. So the everyone asks like what kind of product you made, simple product, or what kind of simple solutions you provided for the real life problems. So you can actually while doing all the coursework, you can for every coursework you can try to like make some very beautiful project for each coursework, and that's going for you very useful. Like you learn lots of things for that project. For example, if you're reading the very simple computer vision classes, then you just try to find what kind of problem I can solve and what's the use of that problem, and then try to implement very simple network or simple algorithm for that problem. So I would say like read as well as you try to implement things. Yeah. And also like you should participate in some kind of challenges. There are like so for computer vision, I would say like there are many famous conferences like CVPR, ICPR, and ICCV. So you should know about these conferences. If you know about these conferences from the bachelor, then actually this is very useful, because when I was in bachelor, I didn't know about these conferences. So when I went to masters, then I realized, okay, these conferences are really, really very good. So, if you go to the website page, you can see like there are many challenges. So challenges means like they propose some problem and they provide the data set, and you have to solve that problem, and they check the accuracy and if your accuracy is quite high compared to the other participants, you win some kind of prize. So that kind of competition is like very, very important for the people who are working in the AI and computer vision or computer science also. So yeah.
Thank you, sir. One more question we'll take from Namrata. She's saying, "Good morning, sir. Can you please explain that while studying astronomical data like images from satellites and all, can we make use of LIGAR technology, or are there some better CV models for studying astronomical data?"
I think I'm not sure like what technology the satellite they use, but whatever the technology they use, but the output is the point cloud data. If you download them, you can get like either high resolution images or the point cloud data. But these days, people are using the point cloud data more than the high resolution images. And the another part of the question is like, what is another part? Like what technology we use to process those. So the technology is basically you can simply use like as I said, like you can simply find first you can try to visualize how it looks actually in the code, and then try to process them by using some deep learning method, very simple deep learning method. Or you don't need to even use deep learning method. You simply start with kind of feature extraction based method. So you can try to extract the features by using without deep learning. There are also some algorithm which extract the features, and then you try to find some object inside that satellite image. So for example, if you want to identify some city, or you want to identify some kind of particular location in that image, or you want to check what is the percentage of the greenery or something like that, you can do with the simple methods and then move to the deep learning based method. I hope
Okay, thank you, sir. We'll take one last question by Shivanshu Rajput. He says, what about the worst case of this algorithm? That is, if the object that you're searching wasn't present in the scene, then this algorithm would transverse every pixel of the scene. How does this algorithm overcome the worst case scenario?
I would say that's a very interesting question actually. So yeah, that's like uh, so far what the algorithm does. So if the object is not inside the image, so if you're searching for some object, for example, if our algorithm is searching for some chair or some cup, then it try to find the cup. If that cup is not the environment, it keeps searching for the cup until the maximum number of steps. So we fix the maximum number of steps. If the algorithm is going beyond that maximum number of steps, we ask the algorithm to quit searching. So that's kind of very that's the one way which we are doing right now to solve this problem. But there can be more smart way to say, okay, so even in the case of the human, if you search for your wallet inside your room, you search for some time, and if you do not find, you quit, you do not search. Okay, you maybe wallet is not inside the room. That's the how we are now training this robot or this algorithm to search for some particular time, and then if you cannot find the object, you just quit. So that's the simple way which we implemented this time.
Thank you so much, sir. The future of computer vision surely promises some mind-blowing and incredible discoveries, along with surprises waiting to unwrap themselves. And we are so glad to have you answer our questions and explain these topics in such a nice manner. Thank you so much, sir.
Yeah, thanks a lot.
Thus, we are obliged to have such an exemplary mentor such as yourself acquaint us with this field. I would like to make a slight mention here to all our viewers that Dr. Onkar Krishna has published many research articles in international journals, spoken in about 10 plus IEEE conferences, and many other reputed institutions across the world. It is our honor and privilege to have such an eminent and experienced speaker in our midst. He has given a vibrant insight to the field of computer vision.
That was certainly interesting. We cannot wait to get a hands-on experience on computer vision. Surely the attendees are also motivated to do the same as well. Thank you, sir.
Thank you so much, sir.
Yeah, let's keep in touch. Yeah, thanks a lot. Thanks a lot for the
Thank you,
organizers.
sir.
Yeah, all the organizers and everyone who attended the talk. Yeah, let's keep in touch.
Yes, sir.
Yeah.
Let us now take a break till 12 p.m. We'll be continuing with the most alluring session panel discussion with industrial speakers. They will be guiding us and discussing the applications of AI and its implementation. Stay tuned.